Thanks for being here at 9. So we can continue. Do you want to save changes? Sure, we'll save changes. Okay, take a seat, you guys. Settle down. Come in quietly, please. All right, so now I'm going to cover some more confidence intervals. And remember, everything in Chapter 9, confidence intervals, we are dealing with numeric variables. And this time we will have 2 samples. Okay? So before we took the break, we did confidence intervals, numeric variables, 1 sample. Now we're going to do confidence intervals, numeric variables, 2 samples. Okay, and the idea here is we take 2 samples. Okay, each from different populations. Okay, and then we create a confidence interval for the difference between the population means. mu1 and mu2. Okay. So here's the formula. Okay. It's going to be x bar 1 minus x bar 2 plus or minus t star times s1 squared over n1 plus s2 squared over n2. Slightly ugly formula. There's nothing we can do about that. Okay? Okay? Degrees of freedom is equal to n minus 1 using the smaller n, using the smaller of n1 and n2. Okay, let's just talk about labels. Of items in the confidence interval. Okay. X bar 1 minus x bar 2. This is also known as our observed difference between samples. Observed difference between means. Okay, yes?
Professor, the formula in the square root, after s12 on the right, after the plus sign on the right, would say s2 squared?
Yes, so this is s1 squared and this is s2 squared. Okay. Observed difference between means. This also is the center of the interval. Or our point estimate of mu1 minus mu2. Okay. T star is our critical value. This s1 squared over n1 s2 squared over n2. This is our standard error. And then t star times the standard error is always our margin of error.
Standard error 2 or 1?
I'm sorry?
You have S2 1 over
S2, where are you talking about? Sorry.
And the square root?
Inside the square root right here? S2 squared. Okay. So you have, because we have two samples, right? So here, let me just list off. So in the problem, the data you see, or you should identify, there are 6 pieces of data you need to identify in your problem, okay? So from sample 1, you need N1, you need Y bar 1, or I'm sorry, X bar 1, and you need S1. And from sample 2, you need N1, I'm sorry, N2, X bar 2, and S2. Okay, so you need these 6 pieces of data inside your problem, and you're going to plug them into your formula to get your confidence interval. Okay. 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 The resulting confidence interval is an interval for the difference between population means. Give you guys a moment to get everything written down. We'll do a quick exercise and we'll move on. Wish we had more time, but we don't. But again, just keep in mind the general principles of confidence intervals that you learned in chapter 6 and we just covered 20 minutes ago. Those same principles apply here. Okay, it's just the only thing that's changed are the formulas. Okay, so if you have these written down on a piece of paper, if you understand the concepts behind confidence intervals, as long as you have these formulas written down on a piece of paper, you should be fine. Okay? The concepts, that's the hard part. That's the part you need to learn. That's the part I'm trying to explain. Yes, the calculations are important, formulas are important, but you can write those down on a piece of paper. I'm not trying to get you guys to memorize all of these formulas. All right, can I go to the next slide? I'm going to count in my head, and then I'm going to go to the next slide. And if you're too slow, you can always watch these videos again on YouTube, pause it on a page like this. Okay, here we go. Okay, so let's do an example. Okay, we want to know the height difference between the average man and average woman. Okay, so one of these we're going to have to label, so we're going to take, we gather data, so we gather data from random samples. Okay, so we survey, we'll say 25 men. The average height of these 25 men is we'll say 69.5 inches with a standard deviation of 3.1 inches. Okay? With apologies to our international friends who have no idea what these numbers mean. Okay. It's average American height-ish. Okay? We survey, we'll say 20 women.
Is it 31 or 3.1 inches?
3.1. It would be crazy if we had a standard deviation of 31 inches, okay? We surveyed 20 women, again randomly selected, okay? Random samples. The average height is 64.1 inches with a standard deviation of 2.8 inches. Okay, so let's, and the instructions will be make a 90% confidence interval for the average, or for the difference between mu1 and mu2. Okay, so let's go through our problem and identify our data. Okay, so just arbitrarily, we've got to label one of the samples men and the other one, and the other one's other sample women. Okay, so just arbitrarily, I'm going to say sample 1 will be the men and sample 2 will be the women. If you chose sample 1 as women and sample 2 as men, that is fine. It doesn't matter. You just have to arbitrarily label one to be sample 1 and the other to be sample 2. Okay? So N1, we need to identify N1, Y bar 1, and S1, and we need to identify N2, Y bar 2, and S2. If you do this step, sometimes it feels like it's extra work in the middle of a problem and you've got to rush for time or something. Don't think that, okay? Take 1 minute and figure out, label all of these things. Label all the numbers, N1, Y bar 1, S1, N2, Y bar 2, S2. It will make your life much, much easier than trying to just read the problem and pick all these numbers out in your head. Okay, so what is N1? N1 is the size of sample 1. So what is that?
25.
We have 25 men. What is Y bar 1, the sample mean of the men? In our problem, 69.5, and the standard deviation, 3.1. And 2, what is that? 20, we surveyed 20 women. Y bar 2, 64.1. S2, 2.8. Good. How are we feeling? Okay, all we got to do now is just plug all of this stuff in into the equation y bar 1 minus y bar 2 plus or minus t star times the square root s1 squared over n1. You probably don't need to rewrite this formula because it should be in your notes already, okay? So I'm just writing it here so we can all see what we're doing, okay? All right, so I'm going to just plug in all the numbers that I have. 69.5 minus 64.1 plus or minus, I'm going to just leave in t star times this standard error, 3.1 squared over 25 plus 2.8 squared over 20. Okay, the rules for finding t star, we have what percent confidence? 90% confidence, and degrees of freedom is equal to n minus 1, where I use the smaller of n1 and n2. So what do I use? I'm going to use 20 minus 1, so I'm going to do 19 degrees of freedom. Is that okay with everyone? Okay, right, you have n1 and n2, you just use the smaller one, n minus 1. 19 degrees of freedom, 90% confidence. What do I have? 1.729, right? So T star is going to be 1.729. Is that okay? So I'm now going to plug this in, and I'm going to punch all of this into the calculator. Let's do 69.5 minus 64.1. I get 5.4 plus or minus 1.729 times everything inside this thing. So it's 3.1 squared divided by 25 plus 2.8 squared divided by 20. And then I take the square root of that, and I get 0.881. 8811. Have I lost anybody? Is everybody doing okay? Okay, you don't have to punch everything into the calculator right now. Just trust me that I did it right, and we got 0.881. You can follow along on the calculator if you wish, okay? Okay, but just, I'm assuming you guys know how to use your calculators now, and if not, you know, we can, I guess, work on that. But, okay, so we have this, so I'm going to multiply that number by 1.729 times 1.729, and so my margin of error is 1.523. So I'm going to have 5.4 plus or minus 1.523. Okay, so I'm going to get a lower and an upper. So I do this plus 5.4. I get and I get 3.877. Okay. So I get this as my upper and lower bounds of the confidence interval, and I would write something like this. I am 90% confident that the height of the average man is between 3.877 inches and 6.923 inches taller than the height of the average female. Or I should say, if I say man, I should say woman. Okay? So I am not making a confidence interval about men in general or women in general, but the height difference between men and women. Okay? So I'm saying if you took the average height of men and the average height of women, I'm confident, 90% confident, that the average height of the man, or average height of all men, is between 3.877 inches and 6.923 inches taller than the average height of women. So basically, I'm saying that I'm 90% confident that that the average male is somewhere between 4 and 7 inches. I'm just rounding off grossly, okay? Rounding off grossly to say, I'm saying that the average man is between 4 to 7 inches taller than the average woman, okay? Now, of course, any individual man, any individual woman will not be exactly have a height difference of 4 to 7 inches, okay? You might have a short man or a tall man, short woman or tall woman, and so, you know, if we picked LeBron James and, I don't know, some other woman who's not as tall, you're going to have more than a 7-inch difference, okay? But this is about the average male, so if we took all men and we calculated the average height of men, and we took all women and we calculated the average height of women, and we took the difference, we would be 90% confident that that difference is between 3.877 and 6.923. Is that okay? So if I said, do we have evidence, I'm going to go to the next slide, do we have evidence that the average male is taller than the average female, what would we say based on this interval? Okay, so let me just, I'm going to copy this. Oops, you don't want to do that. So someone says, do we have evidence that, we'll just say there is a difference between mu1, average height of males, or average height of men, and mu2, average height of women. We would say, do we have evidence? Yes. And what provides that evidence? The value, what? 0, okay? Because if the value 0 were in our interval, then that would indicate that there's no difference between the heights because the difference is 0, okay? So the value 0 is not inside our interval. This provides evidence that there is a difference. Is a difference between mu1 and mu2.
So we should get 0, the value is 0.
0, okay. So to say two things are equal, or to say that there's no difference between two things, that means the difference between them is what? 0, okay? To say two things have the same value means that the difference between them is 0. That's where 0 is coming from. Because the question is asking, is there a difference between men and women? If someone says there's 0 difference between a man and a woman, which is not true, but if there was 0 difference, then there would be no difference, okay? So when it comes to things like height, is there a difference between the average man and average woman? The answer is yes, okay? Now if we brought about some other aspect of life, okay, the difference might be 0, it might not be 0, okay? So if we did IQ scores or something like that, you're probably not going to find evidence of a difference, at least not in the United States and most Western nations where there's equal access to education for men and women. But across, globally, we will probably see a difference because in some places there are restrictions to women gaining education, and that affects overall measures of intelligence. So, okay. So anyway, this is what we have. Is this okay? So on the flip side, okay, so is that if 0 is in the interval, we do not have evidence difference between mu1 and mu2.
What do you mean by flip side?
I don't know. That's a slang term in English, and I don't know how to explain that. Yeah, on the other hand, another possibility, okay? So let's just... see you on the flip side. That's another thing somebody might say if you were in 1995, and we'll see. Okay. All right. Let's keep going on here. Okay, so now we're going to do hypothesis testing, everybody's favorite subject. Okay. Again, everything we're doing in this week is numeric variables versus last week where we only dealt with categorical variables. Okay, numeric variables, one sample. Okay, your null hypothesis. Here, maybe I'll put this in red to indicate that it's important. Your null hypothesis will always be in the form mu equals some number. Okay? Mu equals 30. Okay? Not necessarily 30, but always some number there. Okay? The alternative is going to be identical, except maybe it's going to have not equal to 30, or greater than 30, or less than 30, depending on how the problem is written. Same concepts as before, right? So null hypothesis always has equal sign. Alternative hypothesis is identical to the null, except the equal sign has been replaced with not equal, greater than, or less than, right? This should sound familiar. All right. Okay. So when we were dealing with proportions, what do? We have to figure out what value, and then another value, and then another value. What did you have to do? The standard error. So same type of thing. We're going to figure out our standard error, and then once we get our standard error, what do we find? The test statistic, okay? And then once we get our test statistic, then we look it up to get our p-value. Okay? So this process is identical as before. The only thing that's changing is the formulas for the standard error and test statistic, okay? But the process is the same. So if you got the process down, you should be in good shape. If you don't have the process down, then you need to learn that, okay? Because you won't do well in the class if you don't understand the process behind hypothesis testing. Okay, so let's talk about the formula for the standard error. You're going to deduce S over the square root of n. It's easy, all right? Test statistic. So the standard error is S over the square root of n. Test statistic, okay? It's not a z, it's this time a t, because we're using the t-table, okay? So last week our test statistics were always z. This time our test statistics will always be t. It's going to be x bar minus mu, or mu 0. Where does this mu 0 come from? The null hypothesis, right? Just like last week, right? You had p0, or the p from the null hypothesis. Same thing, okay? So mu 0 comes from the null hypothesis. So it feels like we're covering a bunch of stuff today, and we are. However, it shouldn't be new, right? It should all be familiar, okay? And then you do x bar minus mu 0 from the null hypothesis divided by the standard error. That gives you the t, okay? So you look up to get the p-value. So, what's that?
The mic is dead.
My mic is dead? My mic is dead? Okay. Okay. Okay, how's this? Okay, great. Okay, so once we have, okay, please focus. So now we look up to get the p-value. What table do we use? Okay, use the t-table. Use the t-table, and do we remember how to use the t-table to get p-values for the hypothesis tests? Okay, is the very first thing we did today. We're not going to get exact values, but we get a range for the tail area, right? So you use the t-table, okay? You get a range for the tail area. Okay? And this is how it works. If the alternative has a greater than sign, then your test statistic t should be positive. Okay, and your p-value is equal to your tail area. So remember when we covered the use of the t-table this at the beginning of class, I only talked about getting your tail area. Okay, so this is how we go from tail area to a p-value. Okay. If the alternative hypothesis has a less than sign, then t should be negative. Okay? And in that case, the t-table only has positive values. So you look up the positive value still, okay? Just basically ignore the negative, okay? The t statistic should be negative, but when you look it up, ignore the negative, okay? When looking up, ignore the negative. Okay? And again, your p-value is equal to the tail area. So whatever you get from the t-table, that is your p-value. Okay, and then lastly, if the alternative hypothesis has a not equal sign, then it doesn't matter if the t is positive or negative. The p-value is equal to 2 times the tail area. Okay? So even this should feel somewhat similar to the process we did for proportion hypothesis testing. All right. Is this good?
Yes.
All right, so let's try a problem out. The only thing you need to know really is s over the square root of n, and your test statistic is this, okay? Now, so I'm gonna work through this. I'm just gonna talk everything out, and well, it'll go, okay? All right, so let's say okay, it is believed that the average number of, I don't know, hamburgers an American eats in a month is, what do you think the average number is? 42 hamburgers a month? I am insulted. Okay, let's say, all right, 3.4. Who knows, okay? 3.4 hamburgers a month. Does that sound like a lot or a little? A little? A lot? I guess it depends who you are, right? We know who the vegans are in the room, right? That's a lot. No, I don't know. I have no idea, right? I guess it depends who you hang out with and where you are in the country. But let's just say I'm completely making this data up, okay? All right, so we survey, let's say 40, no, not 40, let's keep it smaller. Okay, let's say we survey 25 random Americans. I don't know how we do this, but we do. Okay, we ask how many hamburgers did you eat last month? I eat too many burgers. I have like a $200 gift card to McDonald's, and I go there like at least once a week, probably more than that. It's why did I tell you this? Okay, all right. The average. I always ordered like cheeseburgers too. The average. So I don't know. I guess those each count as one, right? So my average is probably like 9 cheeseburgers less. Okay, anyway. Okay, the average is 3.9 with a standard deviation of 1.2. Okay? I have no idea, okay? I'm completely making this up, all right? So don't hold me to this. This is fictional survey. I also like In-N-Out. And Carl's. Okay, here. All right, so let's figure out our hypotheses. Everybody loves In-N-Out, right? Except for vegetarians and vegans. But you can get the meatless burger, right? Yeah, I don't. Okay, anyway, don't. All right. Okay. So what is our null hypothesis? Our null hypothesis is mu is equal to what? 3.4, right? It's the value of that we present. Oh, and I didn't ask the question. All right. So I'll say, does this provide evidence? Sorry. That the actual mean is different from 3.4, okay? Oh, we're gonna run out of time. Okay, so mu is equal to 3.4 versus mu what? Not equal to 3.4. Is this okay? Because it just says, does it provide evidence that it's different? You know, they have you heard of like a gift card mall or something? You can get like gift cards to any place, including McDonald's. You can get like a $50 gift card for like $40. It's like 20% off. That's, anyway, okay. It turns the cheeseburger into less than $1. That's, okay. Let's figure out our standard error, okay? Standard error is S over the square root of n. So we get what? 1.2 divided by the square root of 25. I get 0.24. Is that okay? I haven't lost anybody, right? Test statistic is t is equal to x bar minus mu 0 over the standard error. So x bar is what? From our problem, 3.9 minus, what's the mu in our null hypothesis? 3.4 divided by 0.24. Okay? So I get 0.5 divided by 0.24. And what do I get there? 2.083. Okay, what is our degrees of freedom? We're going to have to go look in the T table, right? But we need to figure out our degrees of freedom. So how many degrees of freedom do we have? N minus 1. So we're going to have 24 degrees of freedom. Okay, and we're going to look up 2.0833 in our table. So I go to 24 degrees of freedom, and I find 2.083 in this row is between 2.064 and 2.492. So what do I get for my tail area? What is my tail area? You guys remember how to do this, right?
Between 0.025 and 0.01.
So my tail area is between 0.025 and 0.010, right? So pointing the arrows correctly, I have this. So far so good? So this is from the T table. We remember how to use it, right? So I get my tail areas between 0.010 and 0.025. Is my tail area my p-value? So it all comes to, so check your notes. It says if the alternative hypothesis has a not equal sign, what do I have to do? I'm going to multiply it by 2, right? So all I'm going to do is I'm going to take my, so alternative has not equal, so p-value is equal to 2 times the tail area. So what I'm going to do is I'm going to take this and I'm going to multiply everything by 2, and I'm going to do 0.010 is less than my p-value, which is less than 0.025 times 2. I'm sorry, not 0.010, 0.020. I multiply 0.010 times 2, and I do 0.025 times 2, and I get 0.050. So I get my p-value is between 0.02 and 0.05. Is that okay? I just took 0.010 and I multiplied it by 2 and I get 0.020. And I do 0.025 times 2 and I get 0.050. And so now my p-value is between these two things. Are we good there? Okay, so let's say, let's use alpha equal to 0.05. Okay, is my p-value bigger or smaller than 0.05? It's smaller, right? Here it says the p-value is greater than 0.02, but less than 0.05. So we know that our p-value is less than 0.05. And so what does that mean? Do we reject, not reject? What is our decision? So we reject what? The null hypothesis, and this means we have evidence that the actual mean is different from 3.4. I'll probably eat McDonald's tonight. No joke. I bought it. At a discount, all right? Don't judge me, all right? Yeah, here.
So for 0.010, so multiply by 2,
Uh-huh.
and then you got 0.010.
This should say 0.020, okay?
Okay.
Sorry, my handwriting is bad, and That says 0.020, okay? Oh, you get, yeah, well, anyway. It's because it was, yeah, all right. Okay, is that okay with everybody? So the process is the same as before with the hypothesis testing. Nothing really has changed. The only thing that has changed is the formulas for the standard error and test statistic, okay? So we have one more case, all right? And this last case, again, the same exact process, but here we have hypothesis testing, numeric variables, and this time 2 samples. Okay. The null hypothesis is always going to be mu1 equal to mu2. This is always. Okay? And then the alternative, mu1 not equal to mu2, or greater than or less than. Again, depending on how the problem is written. Okay, so what do we need? We need the standard error. The test statistic. And then we figure out our p-value, and then we make the decision. Okay, so over here, the standard error is equal the same standard error that we use for the confidence interval. S1 squared over N1 plus S2 squared over N2. Just a slightly ugly formula for standard error. Nothing we can really do about it. Okay. Test statistic, T, x bar 1 minus x bar 2 divided by the standard error. Okay. So even here we can see kind of parallels between this and when we did hypothesis testing for 2 samples with p's, right? We had p hat 1 minus p hat 2 over the standard error. Here, because we're dealing with means and not proportions, it's x bar 1 minus x bar 2 over the standard error. Okay. All right. P-value, same thing. This time we look up test statistic in the t-table. Okay, same rules apply for getting, same rules as one sample apply for getting the p-value. Okay, so I don't need to write that again, right? Alternative greater than, if the alternative has greater than, your test statistic t should be positive, p-value is equal to the tail area. Alternative less than, test statistic should be negative, your p-value is equal to the tail area. Alternative has not equal sign, p-value is equal to 2 times your tail area. Same thing, right? Okay, so we have this. So we'll do one last example, and that should cover everything, okay? The hardest part really is figuring out, do we have 1 sample or 2 samples, okay? The problems are going to say, do a confidence interval, do a hypothesis test. You don't have to worry about that. But again, don't mix up the steps for confidence interval with the steps for a hypothesis test. Keep those 2 things very clear and distinct. A common mistake is people try to do the process for a hypothesis test when the problem says do a confidence interval, or vice versa, okay? If the problem says do a confidence interval, follow the steps for a confidence interval. If the problem says hypothesis test, follow the steps for hypothesis test. Don't mix those up. Okay? And then all you have to know is, do I use the formulas for standard error with one sample or two samples? Okay? If you can figure that out, you should be in good shape, because it's just a matter of plugging in numbers here. All right, so let's just do one thing. Okay, so we want to know if there is a difference between the average strength of, I don't know, wood beams. Okay? So we take, we'll say 20 samples, or 20, I'll say 20 randomly selected beams of pine, okay, and the average strength, or the average strength where it broke, was, I don't know, 95 kilograms of force, with a standard deviation of 12 kilograms. Okay, so I don't know. We're just having, this is what I'm imagining here, and I don't know. We're gonna just take little beams of wood, right? And we're putting them on some kind of bricks. And then I'm gonna put 95 kilograms, and then it breaks, right? So that's how I don't know. I'm just making this up, okay? If this is not a good way to test the strength of wood, too bad. This is what we're doing here, okay? So then we take, we'll say 20 randomly selected beams of oak. Okay, and then we'll say the average strength of breaking is 109 kilograms of force with a standard deviation of 16 kilograms. Okay. Okay, so, well, we might run out of time here. Okay, so just like every other problem, it's good to identify your data. So we'll say sample 1, and you just arbitrarily have to pick one to be sample 1 and one to be sample 2. So I'm going to say sample 1 is the pine. You have a question?
No.
Oh, yeah, I got to say, does this provide evidence that oak is stronger? We'll say that, okay? Does this provide evidence that oak is stronger? Okay, so let's so yeah, thank you for doing that. I've been forgetting to write that. Okay, so we got N1, S1, and I'm sorry, N1, Y bar 1, or X bar 1, and S1, and N2, X bar 2, and S2, okay? So in the interest of time, I'm just gonna fill all of these in, reading this, 95, 12, 20, 109, 16, okay? And then, so our null hypothesis, I said, is always going to be mu1 equal to mu2. Our alternative So if mu1 represents the pine, and mu2 represents, or sample 2 is the oak, how do I write, does this provide evidence that the oak is stronger? Do I want not equal, less than, or greater than? I want mu1 to be less than mu2, right? Because we want the mu2, the oak, to be stronger. Okay, so at this point, and I hope it's okay that I'm not going to go through all of the calculations, but at this point you just go back to the other page, right? And you just take all of those values and you plug them in to get your standard error. Then you use that to get your test statistic, and you look it up in your t-table to get your p-value. And the same process there applies. Okay? We have a question. I'm sorry? Roll? I have not taken roll. I've been negligent in taking rolls, so we'll figure something that's fair for everybody regarding the roll. But okay, so anyway, you go through the process and you get that, and it works out. Okay, so I will try really hard again to get a practice quiz posted earlier on in the week, so you guys have practice and opportunity to work on that. Okay, we'll see you guys next week.
Have you ever done the cheeseburger with a Big Mac sauce?